Yeah, so what's quantum about? Well, quantum, the original motivation was to really understand things at a very small scale. So it helps to kind of think about different scales of things and different numbers associated with, different objects that, might or might not have quantum mechanical properties. So as a sort of example here, you have the object and then the size in meters, say. So the universe is about 10 to the 26 meters across. The Milky Way. Oh, there's a question in chat. Oh yes, where will the homeworks be posted? Canvas, and no, they are not from Bellac. Some of them are, some of them aren't. I make up my own homeworks, from various sources, and yeah, there'll be a PDF and a text file, and it will just be posted on Canvas, and I'll let you know about that. All right, so the Milky Way is, about 5 times 10 to the 20th. The Earth, the Earth is 10 to the 7th. A human is about 2 meters, and an insect, might be 0.01 to 0.001. And now we're starting to get to the scale of things where quantum mechanics first sort of appears and starts to have a much bigger role. For instance, a virus, 10 to the minus 7th meters. And already here, already here things get a little bit more quantum mechanical. And for instance, they're able to show 2-slit diffraction patterns with objects, about the size of viruses. And then, of course, where quantum mechanics really becomes important is at the atomic scale, which is what most of the examples are in this class. Hydrogen atom, important one. And of course, there's subatomic structure, the nucleus, 10 to the minus 14, and the proton, 10 to the minus 15. So, around here somewhere is where, and we're constantly pushing this boundary of where quantum mechanical effects, like weird quantum mechanical effects that are unexpected, sort of from our classical intuition, because we sort of live here, in terms of our conception of things. This is, quantum mechanics really starts to play a big role in have significant measurable effects at those length scales. An important aspect here is that you probe things with, when you take a measurement or when you see things with your eye, you are probing them essentially with electromagnetic radiation, which is photons, and we know that photon energy is given by h bar times the angular frequency, or h times the frequency of the photon, and which is also h times the speed of light divided by the wavelength of the light. And this is sort of the size at which we can use the photon. So this is the size, we can use the photon as a probe of objects of this size or larger. This sort of resolution which we have. So that tells us that there's a connection, of course, between the size of which we can probe and then the kind of the energy of the photon that we should use in order to probe it. So things like the atom, the nucleus, things like that, Those would correspond to X-rays and gamma rays and things that we can observe with a light microscope, like some extent a virus, definitely an insect. That, of course, is sort of light that we're used to, light waves, these, X-ray, and gamma ray. So there's a connection, of course, between the kind of probing radiation that you would use and the scale of the object that you're probing. Of course, at things above human scale, you would get radio waves. Would probe things in this sort of scheme. So, but really, quantum mechanics, deals with things on the atomic scale, and it's where we'll spend most of our time working. And so there's some nice sizes related to that. One size that's sort of worth knowing is, for instance, in salt. You have a crystal of sodium chloride. What's the kind of spacing between atoms there? And that spacing is about 0.56 nanometers. So again, it's this sort of atomic scale, the scale of atoms in a solid and things like that. That's the sort of nanometer scale where most of our examples for quantum mechanics will come from. And also, it's convenient to express this in terms of angstroms, which a tenth of a nanometer. And so we'll talk a lot about objects on the sort of angstrom scale. So again, an atom, itself it is about the size of an angstrom. So what else? We'll talk a lot about just atomic structure in general and particle decay, for instance, which is a place where quantum mechanics plays an important role. So I'm going to clear this if that's okay. Yes. So let's see. Sorry. There we go. Okay, so let's see. So one place where quantum mechanics plays a big role is in particle decay. For instance, we can think about the decay of a neutron into a proton and an electron and a electron antineutrino. And the question is sort of, how does this, so this is an observed decay. A free neutron will decay into a proton and electron like this. And you might wonder, can we think about the neutron as like a combination of these three? Is a neutron, somehow some, compound object consisting of these decay states bound up together, and then it breaks up into those three things? And the answer is no, it's not. And quantum mechanics is the method by which you can sort of argue that that's not the case, and that these particles in the decay must actually be created spontaneously. So how do we understand some of that? So first of all, what we can do is we can think about the energy associated with the left and right hand side of the decay. So the binding energy associated with having some constituents. So what's the binding energy associated with having a compound object with two different constituents, x1 and x2? Well, you would, and this, this total object would be some x. Well, the binding energy would be the mass of the two minus the mass of the compound, c squared, rest energy. And for instance, for this decay, the mass of the neutron is bigger than the masses of the constituents. And it's also worth knowing what these masses are. This will come up a lot too. The mass of a neutron is about 900. It's about 0.51. And it's nice to have units to use this E equals mc squared formula to write masses as energies, which is mega electron volts divided by c squared. It's a handy unit to have. So yeah. So what can we say here? So
so I do have a question. So in order for things to decay, they can't be like, for instance, they have to, like, this is made of quarks.
Yes.
So they have a certain charge, and the neutron has a neutral charge. What we're trying to say here is that in order for things to decay correctly, they have to have a greater mass than all the parts added together. Otherwise, it can't work the other way around.
That's right. And in fact, you can check that if you have, say, an atom or like a deuteron, which is a proton and neutron and an electron. You have a proton and a neutron and an electron. We're whizzing around. Then if you calculate the masses of those constituents, then you will find that the mass of this deuteron is going to be less than the mass of the constituents. So this doesn't decay. That's right. But even during the decay, you can ask, does it make any sense for us to think about in this decay? So this is for a decay. Does it make any sense for us to think about the constituents as kind of living in there and just the neutron falling apart into these constituents? And it doesn't, because the neutron itself, the size of it is about 1 femtometer, right? And if you confine an electron in there into 1 femtometer, then according to the uncertainty principle, you would find that the uncertainty in the electron momentum, right, it would times the uncertainty in the position, which if it's living in 1 femtometer, that would be about h Planck's constant. And it will tell you from here that the uncertainty in the momentum is about, you can calculate just from using 1 femtometer and the value of Planck's constant, that it's about 1 eV meter per second. That's the uncertainty in the momentum. And you can convert that, of course, to a kind of kinetic energy associated with that uncertainty in momentum, which is the uncertainty in momentum squared divided by the mass. And what you would find, and this is another place where so this is an important number. Sorry, this is, a little bit, sorry about that. So this is, Yeah, this is let me. I think. Sorry, Sorry, this is the mass of an electron. The mass of the neutron is about. It's like it's almost 2,000 times larger. So this is 938.
So I usually get in the kilogram mass, which was like, yeah, but it's like 9 for the mass of the neutron. I thought it was like 939 point something or 1.67
Yeah,
times
yeah,
negative
yeah.
27 kilograms. It's just the opposite of a proton or neutron.
Well, that's right. Well, but the neutron and the proton are roughly the same mass, at least compared to an electron, which
Yep.
is much lighter. So the electron is about 1/2000th of the mass of a neutron and a proton. So
I
yeah,
mean,
sorry.
yeah, because an electron doesn't have any, it's like what they call femtological or something, because it doesn't have any little parts to it like quarks. But protons and neutrons are made of quarks, so they can break down.
That's right. That's right. That's right. So my point here is that when taking into account masses for decays and figuring out whether or not a decay happens, the proton and the neutron are the ones that are really contributing most of the mass. The electron is quite small, is 1/2000th of the neutron and the proton. And the other point is that if you have a decay like this that's allowed, that you observe in nature, and if we use quantum mechanics to try to understand it, so, like the uncertainty principle, which we'll study in the class, you can ask, does it make sense that the neutron is actually composed of these objects? And if it were, then the electron would have to be confined in a 1 femtometer region. And if it is, then it would have an uncertainty in its momentum, which you can calculate as 1 electron volt meters per second. And if you convert that to a kinetic energy, what you'll find is that the kinetic energy associated with that is 10 to the 5th MeV. A huge kinetic energy. So it's not possible. If the neutron really was composed of those objects, then the electron in there would be whizzing around so fast that it would just break apart the whole object, because the energy scale associated with the momentum uncertainty is so much larger than any kind of scale of any kind of binding energy for the
Okay,
object.
so you're saying the strong force though, because I thought that's what keeps it together, because you talk EVs inside the nucleus versus the outside, which is MEVs, and I thought the strong force is what keeps everything together.
Yes, but the strong force keeps together the quarks. A neutron is
Yeah.
composed of quarks, and it's the quarks that undergo a transformation, and the electron pops out of nowhere. You can't say that the electron is living inside, with the quarks hanging out with them.
I see what you're
According
saying.
to quantum mechanics, that's never going to work, because you can't confine an electron to a 1 femtometer region, right? It will just come apart. And that's what quantum mechanics teaches you, like just using the uncertainty relation. So that's the kind of thing that we'll talk about. The uncertainty relation, where does H come from, and so on. So yeah, but this is a kind of fun application of the uncertainty relation, which we'll study quite a bit in the class, but you should have seen it at least, in undergrad, that the uncertainty in position times the uncertainty in momentum is, about the Planck's constant. Okay, and it's important. I'm bad at these units because I'm not, I'm a biophysicist, so I don't have a spectacularly good intuition for atomic scales, but it's worth knowing the masses of the electron, the scale. So, you can sort of, so roughly, right, the mass of a neutron is in 1,000, MeV per c square, and then an electron is about half an MeV. And they're useful things to know, the masses and the sizes of things. So again, an atom is about an angstrom. A neutron is about a femtometer. So it's just, and those are the scales where quantum mechanics, plays a huge role. All right, any questions before I clear this? And my handwriting will improve over time. I'm a little bit rusty. It's been a while, but we'll get better. It'll get smoother as we sort of go. I'm also sort of getting used to having to present online and in person. It's a little tough. Any questions though? Okay, so what's the sort of history of quantum mechanics? Probably the first place, where quantum mechanics appeared as a solution to a kind of physical mystery is when Max Planck in 1900 was studying blackbody radiation. He was trying to understand if you have an object at some temperature T, what is the spectrum of light that it emits? So there's some power per unit area that an object will emit, and we can call that U omega T. So it'll depend on the temperature, it'll depend on the frequency of the light that we're observing that's coming out, some angular frequency omega, and you just want to understand what the power spectrum is for that. And if you think about it, a black body, what's a black body? It's something that's a perfect absorber of radiation. And why is that, an interesting thing to think about? Well, because if you have two objects, that are at temperature T, then we know if they come, into thermal equilibrium with each other, then the amount of power that this object emits, so the P out, must be the amount that it receives, P in, right? Because otherwise it'll heat up or cool down. So if it's a perfect absorber and it absorbs everything that hits it, any radiation, then it must also be a perfect emitter. And so it's, he was trying to understand how an object, a perfect absorbing object, would emit light. What's the power spectrum, associated with emission from an object at temperature T? A black body meaning a perfect absorber. So it's a kind of ideal case where if you're a perfect absorber, then you also must be a quote unquote perfect emitter. So you wanted to know what's the sort of fundamental spectrum associated with that. And so the way he thought about it is, if it's a perfect absorber, then you can think about the black body as a kind of a box. And in this box, you might drill a little hole, and any light that hits, the hole would get captured and sort of rattle around in here. So you can think about light in a sort of a perfectly absorbing container. And you can think about what's the sort of thermal energy associated with having radiation living inside this box. So this is a box of electromagnetic radiation. And so inside of here, you could posit that there's an electric field, and it'll be some plane waves. Radiation just bounces around in there, so there's some polarization. There's some wave vector associated with the electromagnetic wave. Here's the angular frequency. And so K is the wave vector associated with the propagation of the wave, right? And then the polarization is this E naught vector. That's kind of what it looks like, and it's rattling around in there. And if it's confined inside this box, then your K can only have particular values. If it's a cubic box, right? If it's got a box of size L, then in order for the electromagnetic radiation, the electric field to vanish at the box boundaries, then the wave vector k can only have this particular form, where it has discrete modes, where these are integers. And so this is sort of what he was thinking about, and what he recognized is that for each value of these integers, that would represent a different kind of standing mode right inside the box. So like for n equals 1 along the x direction, you have this kind of mode, and you would have oh sorry, no, for this is be like this, and then you could have higher order modes with larger n, but fit more wiggles inside the box, and the only condition is to sort of vanish at the boundaries, and so on. And so each of these would have and then the angular frequency of all these is just c times the magnitude of the k vector. And that's also the energy, of course, h bar omega. So there's an energy. Let me just put the h bar here. So there's an energy associated with each of these modes. And what he recognized is that, well, each of these modes is some degree of freedom within the box. You could have a standing wave in each one of these modes. And so according to equipartition, each of these modes should get a kT of energy. A mode of the EM field inside the box gets 1 kT of energy. And well, that's bad, because then, since in principle, the ends are unbounded, there's an infinite number of them, then the energy, what's the energy of the waves in the box? Energy of the waves in the box. The average energy would just be kT times the number of different modes you have. Well, there's an infinite number of modes. So you run into a big problem. The average radiation energy inside this box diverges. And, well, he couldn't figure out how to resolve it, so he decided that instead of being able to have instead of just having any mode here and having all of them contribute, a trick that he did, which for him was a mathematical trick, he just decided that perhaps at each value of omega, maybe the energy is quantized, in the sense that the actual energy associated with a particular omega is quantized into some units, that there's some n number of them, and each one of those units, which later became photons, has an energy of h bar omega. So that's, oh, sorry. So this is what I meant to say. Okay. So if you assume that each mode here with frequency omega, let me just parse this out a little bit. All right. So here we go. Let me parse this out. So this is sort of the classical result, and here I'll put and this is also classical. So, and this is a solution. This is the quantum mechanical solution to the problem will come here. So, okay, so again, we have these standing modes, and in principle, there's an infinite number of them because n can be arbitrarily large, and so each one should get some amount of energy kT, and there's an infinite number of them, so the energy of all those is just kT times infinity. But what Planck decided to do is he said, well, maybe the energy associated with each particular mode is quantized, that there's n times h bar omega for each particular mode. And so for a single mode, the probability of observing a particular energy at that particular frequency, omega, is going to be given by this. So a particular energy, since it's quantized, the different possible energies are just given by n, which is an integer, times h bar omega. That's the n number of photons with frequency omega. And so if it's a thermal system, then the probability of observing this particular energy must be given by the Boltzmann distribution. So it's the probability is e to the minus n h bar omega divided by kt. This divided by kt is often just written as beta. And then you sort of normalize by the number of different states that you have. And in principle, there could be, the number of quanta could be anywhere from 0 to infinity. So you normalize by that. And so you sum over n, let me call this m, I guess. mh bar omega over kt. And you can do the sum as a geometric series, and what you get is that the probability of observing this energy at a particular frequency, an amount of energy, En, is just given by this expression. And let me put the betas in, it's e to the beta minus beta n h bar omega. Divided by 1 minus e minus beta h bar omega. All right, because this is a geometric series here. And so what can we do then is we can calculate the average energy. So what's the quantum mechanical fix? The quantum mechanical fix is now that the average energy is going to be a sum over at a particular energy. So again, this is at a particular omega. The average energy at that omega is going to be the number of photons or the number of quanta times h bar omega times this probability of observing that energy. And this is, again, this is En. And this gives you, after some algebra, it gives you h bar omega over e to the beta h bar omega minus 1. And so now this is the average energy at each omega. And so this is the quantum mechanical fix, so that then you can calculate the total energy. And the total energy, instead of being infinite like it is here, that's bad. The total energy is just going to be a finite number. And the way you do it is you sum over all the modes, nx, ny, and z. And but each one, right? Each one will have its own average energy that's given here. And so you just do that. It's what you get is well, let me. So 2 pi. So this is omega here, now written in terms of the k vector. Divided by L. You don't have to worry about too much about this expression. The whole point is that by saying that the energies at for each omega are quantized, they're given by some integer number of quanta. What happens is that it regularizes the expression that you would normally get for, assuming every mode gets a kT of energy. Now you see the temperature comes in here into the denominator. And so at high temperature, where things break down, this expression becomes sorry, at low temperature, when this thing breaks down, it's, so sorry, when you sum over all the omegas, remember omegas is the thing that's related to the nx and y and z squareds. Because omega is just c times the magnitude of the k vector. When you sum over all the omegas, because of the denominator, it regularizes the expression for the total energy. And so that when you calculate this and you get, this result here, maybe it's a better way to look at it. See, so when omega gets big here, then this goes to 0. And it's okay if you sum over all the omegas, because then it's, all fine and good when you sum over all the omegas or all the n's, right? Because it gets regularized. Classically, if you don't have this quantization of, the number of quanta for each omega, number of photons for each omega, then you wouldn't have this denominator. You would just have h bar omega for the energy, and each one of those modes would get a kT of energy, and you'd be done. It'd be very bad because you'd get a divergence in the total energy. But because Planck decided that maybe the energies are quantized for each mode, then he was able to regularize the expression for the total energy and get a finite result. And let me just, I'll just add that, I guess, 2 pi beta h bar c. This is just the omega part, just written in terms of the nx's. Nx squared plus ny squared plus nz squared over L minus 1. And this is finite. Okay. And for him, the introduction of this H was arbitrary. It was just a mathematical trick in order to fix up his analysis of sort of classical radiation in a box. And of course, this is, you learn about this later on, you learn about this in StatMech, so don't worry too much about the expressions. But historically, this is the first place where sort of people recognize that perhaps, there's more to life than just classical physics, or classical electromagnetic radiation, where you just look at standing modes in a box. Perhaps each of those standing modes itself corresponds to some quantum number, to some, integer number of energy quanta or particles, which, eventually ended up, being called photons. Any questions about that? And it's a little bit, this first class is a little bit hand wavy because we're not really doing much. We're just sort of going over some historical motivations and just painting a picture of where quantum mechanics comes from. Any questions though? Sean?
Sounded like somebody said it had a question. Did somebody else have a question? I don't think so, but.
Is this the same treatment as given in like Weinberg at the beginning?
Should be, yeah. Yeah, I didn't really go through the math of this very well, because it's just sort of a StatMech problem, which is not really a topic of the class. But for those of you in StatMech, any classical degree of freedom, a quadratic degree of freedom, will get an energy of kT, a thermal energy kT. And so Planck's problem was that if you had electromagnetic radiation in a box, then every single mode would get an energy kT, which leads to the so-called ultraviolet divergence, which is, just means that as you sum over the higher frequencies, the higher energies, each one gets kT, and so the energy of the radiation in a box diverges. And so what he did was, he said, no, each mode actually has some discrete number of energy units and it could be from 0 to infinity, whatever, but it's discrete, and so that means that for each mode, there's actually a probability distribution of observing a particular energy, and because of that, you actually get the regularization, because it's not so likely that you get a lot of you get a whole distribution for each of the omegas, and at the larger omegas, the average energy coming from those modes gets suppressed as soon as you quantize, each mode into a discrete number of energy units. And so that was his trick in order to fix this problem. And and later on, it was recognized that it's true that each electromagnetic mode is not just like a classical mode. There's actually a quantized, has quantized energy levels, and there's a number of photons that have that frequency for that mode, and that's what these quantized levels ended up becoming, is just photons at that particular frequency. Okay, more questions? Oops. All right, so what else? In terms of motivation. So there's also, Einstein studied the, Einstein in 1905 studied the photoelectric effect. And he was interested in light hitting a piece of material, and he was interested in the light kicking out an electron from the material, and he was interested in what the kind of energy that you would get, the kinetic energy of the electron that comes out. And what they found was that it didn't depend on the intensity of the light. The energy of the kicked out electron was always h bar omega, which is the frequency of the light, minus some constant, which is called the work, the work function. And if you think about it, that's really weird, because you'd imagine increasing the intensity of the light, well, it should presumably create more energetic electrons, right? But it didn't. The kinetic energy of the electrons that got released, and you can introduce some stopping potential to stop the electrons in their tracks, figure out what the actual kinetic energy is, applying an electric field to get them to stop moving. What they found is that that energy is just dependent on the frequency of the light that comes in. And to us, that sort of makes sense, right? Because imagine a photon coming in, interacting with the material and kicking out an electron, and the energy of the photon is h bar omega. And I even used that freely in the last slide, but back then that wasn't obvious at all. That's the way things. That's how things worked, and so it's a kind of amazing result in the sense that it doesn't depend that that in this photoelectric effect that the kinetic energy of the liberated electron is only dependent on the frequency of light. And moreover, it was weird that the same h bar, this h bar, was the same one as Planck used to do his blackbody radiation analysis. And so this was sort of the beginning of quantum mechanics, is actually through the analysis of electromagnetic radiation and light emission from thermal bodies, which is actually quite far from where most of our applications of quantum mechanics will come from. which will have to do with you know, things like understanding the hydrogen atom, things like that. But yeah, any questions about that? That's sort of the birth of quantum mechanics, and then it developed for a while, and eventually in 1924, de Broglie, he decided to adapt the formula that we use for the so again, the photon itself, you know, has a momentum. That's its energy divided by the speed of light, which again is h bar omega over c, which, you know, is h over lambda. And so he proposed, de Broglie postulated that for a massive particle, that maybe you can connect its momentum to some kind of wave-like phenomena with a characteristic, you know, with a wavelength lambda. And so maybe this relationship that, you know, p is related to the inverse of some wavelength corresponding to some wave, then maybe that's true for massive particles as well. And so the idea is that when a particle is in motion, perhaps it has a similar kind of interference phenomena as light waves. And I guess, so kind of running short on time, but that's the idea, this connection that the momentum of a particle is also related to some wave-like phenomenon. We don't know what it is yet. We'll see that, you know, it's related to the wave function of a particle in motion, but you know, that's later. De Broglie anyway just postulated such a thing as possible. And then maybe you could get interference phenomena. For instance, if you pass particles through some slits, if you have some particles moving with some momentum p, perhaps this kind of relationship between the momentum and the wavelength means that, you know, particles have some kind of wave-like interference phenomena. And indeed, that was observed. You can pass atoms through two slits, and as long as you don't do anything fancy to keep track of which slit they go through, they'll behave as if they're just electromagnetic waves that radiate out from each slit, and then, you know, form an interference pattern, form some interference fringes, and only land at certain locations on the screen. That's some distance away. And the intensity here of, say, particles actually coming in and hitting the screen, coming out of these two slits, the intensity is proportional to the kind of flux, and this is, say, the top slit, and this is the bottom slit. And what you can show is that the intensity of the particles here is proportional to the sum of the amplitudes of these associated waves squared if you have no information about which slit the particles go through. And if you do, if you keep track of where the particles go, either in the bottom or the top slit as they come out, then the intensity changes to the two amplitudes squared. And we'll talk about, and these, we'll discuss, in great length what these amplitudes are. There'll be probability amplitudes associated with the particles, and we'll spend a lot of time developing that formalism. But this all sort of started trying to understand wave-like properties of massive particles in a similar fashion as sort of people already understood electromagnetic radiation. Sort of started with de Broglie. And that's you know, we'll talk about the Bohr atom a little bit later. This is a more intro. I think so. Next class we'll talk more of this kind of historical background, but the meat of the class won't really get started until I guess middle of next lecture. We'll start on the actual mathematics, but I wanted to give you sort of hand wavy introduction to historical aspects. But we'll get a little more cleaned up, I guess, next week when we'll really start developing the formalism systematically. But it's good to know about these things, you know, where they come from, where quantum mechanics started, turn of the century, again, studying blackbody radiation, and eventually, you know, the de Broglie's insight that the kind of wave-like interference phenomena that people understood for electromagnetic waves, perhaps, you know, they also work for massive particles like electrons and atoms. And even now, I mean, you can do interference experiments with viruses, as it turns out. You send viruses through double slits, you know. You can also get interference fringes. Yeah. Any questions there? Yeah. Online people?
Good.
Yeah. So keep checking Canvas and stuff. I'll post the Discord link, or I'll email it out.
When will